So temperature calculations, and then we'll get into the first law of thermodynamics. Does anyone have any problems you want me to do? Any of those pressure problems that I gave you? Okay. So temperature. So temperature is like the trickiest of all units. I mean, and it's because the scales have different zeros. So it can be tricky. Because zero temperature means different things for different units. So there's only 4 temperature scales that we'll ever see. Those are Celsius, Fahrenheit, Kelvin, and Rankine. Yeah, we're not going to use Rankine much, but basically, Kelvin is Celsius, but it's shifted so that 0 is absolute 0. Rankine is Fahrenheit, but it's shifted so 0 is absolute 0. So these are the two that have 0 at absolute 0. And so we need ways to convert back and forth between these. The conversions, the Fahrenheit temperature is the Rankine temperature minus 459.67. And so that tells you what absolute 0 is in Fahrenheit. It's negative 459.67 Fahrenheit. The Fahrenheit temperature compared to Celsius is 9/5 times the Celsius temperature plus 32. And then to go from the most common one that we'll have to do is to go from Celsius to Kelvin. And that's 273.15. A lot of times I'll just call that 273, but yes.
So the second equation,
equal Fahrenheit. Thank you. This should say thank you. This should say Fahrenheit. Okay, and the thing that makes this kind of especially confusing is you have to recognize in a problem whether you're talking about an actual temperature describing a state or whether you're talking about a change in temperatures. If you're talking about a change in temperatures, those conversions are different. That's all because of those different 0 points. Okay, no other kinds of units have a thing where you have to make a distinction between whether you're talking about a change or whether you're talking about an actual the property temperature. Okay. So if we're talking about a change in temperature, then a change in the Fahrenheit temperature is the same as the change in the Rankine temperature because they have the same scale. The change in the Fahrenheit temperature is just 9/5 times the change in the Celsius temperature. And the change in the Celsius temperature is the same as the change in Kelvin.
So the change in Fahrenheit is this same as 9/5 Kelvin?
Yes, so right, you could substitute Kelvin in that second equation for the Celsius one. That's right. Mostly, I mean, the only way you're going to use this is to convert to Kelvin. Sometimes you'll get temperatures. Some temperatures will be given to you in Fahrenheit, and you'll have to go to Kelvin. But just remember to ask yourself: am I talking about a change in temperature, or am I talking about an actual temperature? And you can see mathematically how it works. A change in temperature is a difference in temperatures. And so those extra constants just cancel out when you take the difference. Okay. So you're going to have to do a few problems doing temperature conversions just to get used to it. But then the next, sort of the first big topic is the first law of thermodynamics.
Are we going to need to memorize the...
No, you'll never have to memorize any conversions or any equations. They'll all be given to you on the test. And I'm still working on the equation sheet, but I'm planning to give you just a full equation sheet that all the equations that'll be on the test given to you are going to be on this sheet so you can get used to the same format for everything.
Just like in real life.
Yeah, right. Well, in real life, you can just get a tattoo. That's what I've done. My whole arm. And if you're like a really short person, you just can't study as many classes. You can only get up through like Thermo level 3. Okay, the first law of thermodynamics.
So Adam Savage got like a ruler. So I'm like, that's kind of brilliant, actually.
What?
He put a ruler tattoo on.
Oh, yeah.
Goes to the store. He's like, oh, that's what I need.
Yeah, but what if he grew or shrunk? Well, don't do it until you're 18. Maybe that's why they say no tattoos before you're 18.
Yes, that's it.
Okay, so the first law of thermodynamics is conservation of energy. In Physics 1, just to relate this to stuff that you're used to, you had, well, it was the conservation of mechanical energy, and it came from the work energy principle. And different people emphasize that to different amounts. I don't even mention that really in most of my physics classes, but books always have a chapter, a half a chapter on the work energy principle. And what it says is the change in energy is equal to the work done by non-conservative forces. And E is defined as the kinetic energy I'll call that T, plus the potential energy, I'll call that V. I know it's a little annoying that different classes use different letters to represent different things, or to represent the same thing, you know what I mean? But it just has to do with what other variables are going to show up in equations in that class, you know? So in thermodynamics, T means temperature, and it also means kinetic energy. That's a little bit of a pain, but those don't ever show up in the same equations.
Well, that's really the same thing anyway, right?
The temperature, they're related. Actually, that probably makes it worse. They're different but related. And then the WNC is the work done by non-conservative forces. Remember the conservative, non-conservative force thing? So the work done by, remember that potential energy of a conservative force is actually the negative of the work that's done by that conservative force. So the work done by conservative forces are incorporated into this V, and the work done by non-conservative forces are in that W. In this class, you can think of the first law as the work energy principle. But now it's including thermal energy. The work energy principle and the conservation of mechanical energy only work if there's no significant exchange of thermal energy. Now we can deal with it. So what this means is now energy can be added or removed from the system by still work. Remember that the definition of work is a change in energy caused by the application of a force. And now it can also be, this is the new thing, it can also be, energy can also be added or removed by heat. And heat is a change in energy caused by a temperature difference at the boundary. And the second way thermal energy changes this is along with the kinetic energy and the potential energy, E will now include internal energy. So those are the differences. And then you also, maybe the most confusing thing about using the first law, I mentioned this last time, is the odd sign convention that you have to use. So this is a key point. You have to get used to this odd sign convention. Where a positive value of Q means energy is added to the system.
And that Q is a part of E.
That Q is heat, so that goes over on the other side of this equation. So Q and W are ways that energy changes, and over on the left side deals with the the energy itself. So positive Q means energy added to the system, but positive W means energy is removed from the system and used to do work on the surroundings. And I mentioned last time, and I'll draw it again, to remember this, think of the power stroke in a power cycle. So think of a power stroke of a piston. What happens is so the gas is here. That's the system. You heat up the gas, and the result is the piston rises. Okay, and so what's happening in this case is energy is being added to the system through heat, and energy is being removed from the system by doing work on the surroundings.
So really then the full equation is T plus V equals Q plus W.
T.
Right?
So the full equation with this funny sign convention, that would be the sensible way to do it. But with the funny sign convention, what you get is the change in energy is equal to Q minus W, where E is defined as T plus V plus now U, and this U is the internal energy. And how much internal energy the thing has is related to what the temperature of the system is or what phase it's in. If you add energy, you make the temperature go up, or you make the phase change. One thing in this class to keep in mind is, so in this class, very often, most of the time, I would say, the change in kinetic energy and the change in potential energy are going to be negligible. And we're going to be, when we talk about the total system energy. We're mostly just talking about internal energy. Okay, so now all we have to do is figure out how do we know things about the internal energy, and how do we calculate work, how do we calculate heat. You know, I mean, that's a lot of stuff, but this is the equation we're going to use. So the first thing is there's one type of work that we always have to consider. And that's the work of expansion. Um, the systems that we're going to isolate. Oh, question?
Yeah, well, really you mentioned delta H, so like the change in heat, then also you kind of swapped it to U, maybe, or is that
Okay, so
completely different?
so H is something else. H is enthalpy. We'll talk about that later. We're going to always use Q for heat. And I mentioned this last time, and it's going to be worth mentioning over and over again because we're so used to thinking of heat as the temperature, you know, like, oh, this heat, you know, I can't take this heat. I mean, that's just how we talk about heat, but that's not that's not what heat is. Temperature is one thing. Heat is an exchange of energy due to that temperature difference. So thermal energy is, you're going to see, internal energy you're going to see is related to temperature. And that's measured in Kelvin or, you know, Celsius or whatever. Heat is measured in energy, and it's just a transfer of energy caused by that difference. Okay.
So like heat is, we talk about how it's like the vibration of the atoms, but it's
Yeah.
more so like a radially outward force happening.
Say, what is heat or
Yeah,
temperature?
like as you increase the temperature of
Yeah.
an atom,
Yeah.
it's just putting a force outward radially, like spherically.
Oh,
outward from it.
they're just moving randomly, but the way it works is they're bumping into each other, and as they bump into each other faster, they hit the walls faster, and so that's what makes the effect is an outward pressure.
Yeah, but then that like so exactly. For example, like when it changes from a water to a liquid, it's that outward pressure overcoming the intermolecular the forces.
Yeah, that's right.
And that's
They
what breaks apart.
they switch to, they get far enough apart that they don't really have much interaction, intermolecular interaction anymore. They turn into just rubber balls that just bounce off of each other. I was going to say the system that we care about in thermodynamics is almost always going to be, it's either going to be a gas all the time, or it's going to be in a phase change between liquid and gas. And the reason, so we're not going to talk about solids really at all in this class. The reason for that is since this is an engineering class and we're talking about how to harness these energies, there is a huge amount of energy required to go from a liquid to a gas. It's a relatively small amount of energy required to go from a solid to a liquid. And so you can take advantage of the fact that all that energy can be stored in a gas with a relatively low or even a zero difference in temperature, you know? And so we're going to see that we're mostly talking about gases, and it's because they're more useful for engineering purposes. Okay, and so the reason I wanted to bring that up here is because we're going to use work of expansion all the time. Work of expansion is not important if you're talking about solids or liquids. There is a little bit of expansion, but it's very small. It definitely doesn't produce any meaningful amount of work. But with gases, you can get a lot of expansion and produce a lot of work that way. And so, like always, like almost always, think of this as a piston cylinder setup. And the gas is the system that we're isolating. And the work of expansion, W, is equal to the integral from volume 1 to volume 2 of the pressure d volume. And this equation, two things about it. It always holds, so you can always use this. You don't have to think about, am I talking about ideal gas? Like, we're going to end up breaking stuff up into a lot of different classifications. Am I talking about an ideal gas, an incompressible material? This holds no matter what.
I'm sorry, what was the P?
Pressure. And this obeys the first law sign convention. So you can just trust the sign on this and put it straight into the first law. And some intuitive things that you should understand about this. And you can test it out, just put some numbers in and see that it works this way. But the work of expansion is positive anytime the gas expands. It's 0 if the volume is constant. And it's negative if the gas contracts. Okay, well, when can you compute this integral? This integral is always true, but that doesn't mean that you have the information you need to calculate it. So when do you have enough information to compute this integral? Well, what you need is you need to know the pressure as a function of the volume, which is kind of an awkward, that's not a real natural way to have the pressure expressed. But if you can come up with it in this form, then you can always compute that. And it's even easier if the pressure is constant. Okay, so let's do a couple of examples. So first, let's say that we have a constant pressure of 1.3 times 10 to the 5th pascals. And the gas starts at a volume of 0.35 cubic meters. then the temperature is reduced and as a result, the volume decreases to 0.20 cubic meters. So first, let's calculate the work of expansion. And second, if we assume that this cylinder is well insulated, meaning that there's no heat exchange, what's the change in the gas's internal energy? So the first part, we're just computing this integral. We know that the work of expansion is equal to the integral from the starting volume to the ending volume. So we're starting at 0.35 and ending at 0.2 of the pressure times dV. The pressure in this case is constant at 1.30 times 10 to the 5.
And that's the pressure of the gas inside a chlorine.
That's right. Yep, that's the pressure in your chosen system. And so, we can pull the constant out of the integral and we get 1.3 times 10 to the 5 times 0.2 minus 0.35. And we get a work of expansion of negative 19,500 joules. Everything's in SI units, so the energy is going to be in SI units.
Negative?
It does say that, but okay, so now we have the work of expansion. Now we want to know what's the change in the gas's internal energy. Well, we can write this as the change in kinetic energy plus the change in potential energy plus the change in internal energy. And unless you have reason to believe otherwise in this class, we're just always going to assume that those don't change or that those changes are small compared to the other stuff going on. And this is equal to Q minus W this is the kind of stuff where that sign convention can give you kind of fits, but and so what we get, it's insulated, so there's no heat transfer. So Q is 0. And so the change in internal energy is positive 19,500 joules. So will the temperature of the gas go up or go down? If it's not at a phase change boundary, it's going to go up. An increasing internal energy corresponds to increasing temperature or going to the higher phase.
So you said that the temperature reduction is what caused this change in volume? Did I misunderstand that?
First, the temperature is reduced. I did say that. Temperature is reduced. So it would cause, yeah, so that is funny. Let's get that out of there actually, because that's just confusing. So it could work that way. You could reduce the temperature and then the pressure would compress it and that would make the temperature rise a little bit. I don't know how it would compare to its original temperature, but
The temperature on the system is increased, so the temperature of the gas decreases.
the temperature,
No, the temperature of the gas increases.
yeah,
The
it's
system decreases.
the, well, so to make it contract, to shrink the volume in there, you would have to reduce the temperature of the gas, and then the shrinking would cause a change, like an opposite direction of temperature change in the gas. That's
I'm more than
It's-
happy just to erase that.
yeah. Let's erase it. Let's erase it, and actually, let's think of it as like the piston is pushed down. Okay, now it all makes sense.
Thank you.
I have another question.
Yeah.
I'm just wondering how often the condition that no heat exchange occurs. And then also how you would factor in heat exchange current.
Yeah, well, in a problem like this, we will talk a little bit about different modes of heat transfer and how to calculate if there's conduction or convection or radiation, and how to calculate those. A lot of times it'll just say through some other measurement, we've calculated that this much heat is put into the system or removed from the system. And then you would just put that in for the Q.
But we'll have examples where there's no like force being applied. It's just a change in temperature, which results in a
Yeah, right. Yeah. One thing I wanted to say here is I wanted to tell you some of the physical causes of some common assumptions. Okay, so like for example, I said the pressure was constant in this. That's one of the ones that I'll talk about. So here are some of the things that you'll see pretty often. Constant volume. Just means that the gas is enclosed in a fixed size container, or if it's a piston and cylinder, the piston isn't allowed to move. This is called isochoric. You'll sometimes see it given that way. Second, constant pressure. That's also called isobaric, like barometric pressure. And you do that with gas in a cylinder and a constant force is applied to the piston.
Another way to say that would just be like a freely moving piston.
Yep, that's one. You can do it like that, or you can somehow apply like a fixed known force on it, but it has to be free to move to adjust to that force.
The opposing force, you're saying.
Yeah, so whatever the gas is doing, it's trying to expand and contract, and that piston needs to be able to move around freely so that the counteracting force,
So gases want to maintain a constant pressure?
I guess that is true. If they're in contact with each other, they want to equalize the pressure. The high pressure gas will leak into the low pressure gas until they all share the same pressure. If they have a boundary between them and that boundary is movable, then it's going to be like a pushing contest between the two sides of pressure.
Until it's equal.
Or until the thing blows up or
Got it. Okay.
or is compressed.
But for constant pressure, temperature also has to be constant?
Nope.
Okay.
That's not, yeah, right. Because like in this case,
You're changing the temperature.
yeah, so if you had, let's look at this cylinder here. So imagine that the only force applied to that piston was the weight of that piston, okay? And then you heated up the gas in there. The gas would expand, and the piston would rise. But when it came to rest, and I guess we're always kind of assuming this quasi-equilibrium kind of state, that everything's happening slowly enough that everything's kind of at rest at every instant we consider. When it comes to rest, that same amount of force pushing down is equal to the force pushing up from the gas. So the temperature has changed, but the pressure is the same in the gas. Another one that we'll see often is constant temperature. That's called isothermal. And that's caused by the gas being in thermal contact with a large reservoir at a fixed temperature. So you can imagine the cylinder being submerged in a large container of water that's at a fixed temperature. And so that gas, if you're doing your calculation slowly enough, and imagine that the cylinder is made out of copper or something that has good thermal conduction. Okay, so if you press the piston down, the temperature of the gas is going to increase, but then the temperature of the water acting through that copper cylinder is going to bring the gas back down to its original temperature. So that's how you get things to happen isothermally.
And if the piston doesn't move, all of that heat goes into the water with the copper?
Yes, that's right. Into the water, but it's a big vat, so it's just carried away, it's,
Right.
yeah.
But until the temperature is completely changed, it's exerting a force.
So until the temperature, okay, so if you compress the gas and the temperature goes up, and yeah, it's trying to get back to its original size because the pressure is increasing.
But
yeah.
if you hold it, then
Yeah.
the only place that
Right.
has to
Eventually
go-
it'll give up. Yeah,
Okay.
that's right.
Like most things in a tank of water.
Not fish. Okay. Well, let's stop there and we'll just do more first law problems next time, and we'll get into a couple different forms of the first law. And we're pretty close to being able to do a lot of interesting problems. So that'll happen Friday, I guess.